Welcome back everyone. In this lecture, we will see a proof of Weyl character formula using Fradenthal's formula. So, before going into the proof, let us recall what is Weyl character formula, how to interpret them in terms of elements of this group ring or group algebra. So, let us start with a dominant weight lambda. For lambda dominant, so we have this finite dimensional irreducible representation V of lambda. So, this is the finite dimensional irreducible representation of SLN plus 1. So, we know that the Cartan algebra acts diagonally on this V of lambda, that is semi simply on this V of lambda. So, in particularly we can actually write this as direct sum of V lambda mu, where mu comes from lambda plus. And we also define the weights of this V of lambda. So, the weights of V of lambda is defined to be those mu in lambda such that the V of corresponding the muth weight space is being non-zero. So, we already know that this is actually bounded above by the highest weight lambda. So, this indeed lies inside this cone bounded by lambda q minus lambda minus q plus. So, here notice that, so this cardinality of this weight of V lambda is finite because V of lambda is finite dimensional, and each of this V of lambda muth weight spaces, they are all finite dimensional. So, in particularly we can define this character. So, to view the character as an element of some character ring, okay. So, we have want to actually slightly modify the ring so that we can actually work comfortably with all these elements, okay. So, just to clarify things, first I want to actually spend some time on which ring we are indeed working with. Okay, there are various rings that are actually floating around. So, whatever you are comfortable with, you can actually work with that, not a problem. So, we already defined the character ring. So, one can actually work with that if you are considering Verma modules and so on. But now, we are only dealing with the finite dimensional representation. We do not need to go to that character ring that we define. Instead, we can actually work in the group ring or group algebra. So, what I mean by that? So, one can actually take this weight lattice. So, recall, so this is the weight lattice. So, now one can actually take this group ring generated by this lambda over Z. So, this is what it is. This is span of all this e power lambdas, where lambda comes from capital lambda. So, one way to think about it, you can think e power lambda as a formal variables associated with the lambda in capital lambda, and you have this multiplication of these elements coming from this addition of this capital lambda. So, that way you can make this Z bracket lambda into a ring. Okay. So, this is indeed a ring. So, one can actually define e power lambda times e power lambda dash to be e power lambda plus lambda dash for lambda lambda dash in lambda, and you can extend this linearly and then define multiplication in this ring Z bracket lambda. But to work with these characters comfortably, we are going to slightly change our ring. Instead of working over Z, one can also work over Q. So, what we are going to do, we are actually indeed going to take Q bracket lambda. So, this is what, this is again span of, now Q linear span of e power lambdas, where lambda comes from capital lambda. So, this is just e power lambda, lambda in lambda being the basis of this vector space, if you want to think in terms of vector space, and we have this multiplication. Using this multiplication, we can actually make this as a Q algebra. So, this is indeed Q algebra. So, sometimes we can actually work in this Q algebra, or sometimes we need to actually consider elements of the form lambda by 2 for lambda in capital lambda. So, we have to enlarge this algebra slightly bigger. So, we can actually embed this inside this Q bracket lambda by 2 and then work inside this algebra as well. Okay. So, this is actually algebra associated with lambda by 2. So, we are actually considering this bigger lattice lambda by 2, which is actually which contains this capital lambda. Now, sometimes we need to actually invert some of the elements. For example, we know that we need to at least invert the product side of the character formula. Okay. So, if you remember in the denominator identity, we defined this e power rho times product 1 minus e power minus alpha. So, that is the term that will appear in the denominator in the Weyl character formula. So, we have to talk about inverting that kind of elements. So, because of that, so we need to actually slightly move further above, and then we should work on this formal power series algebra that is generated by this e power lambda. Lambda comes from capital lambda by 2. So, basically we will take this formal power series. So, what is this? This is the formal power series, of course, algebra generated by e power lambda, where lambda comes from lambda by 2 over the rationals. So, one way to think about it, so each element of this algebra is going to be a formal power series in the variables e power lambda with the coefficients coming from Q. So, we can start doing all kind of addition, multiplication and so on, as long as the elements that the coefficients that are involved in that computations are all finite. So, we do not need to worry. So, the only thing that we are going to use is the following identity. So, that is what we should be comfortable with. So, if we take for example 1 divided by 1 minus e power lambda. So, this is supposed to be equal to 1 plus e power lambda plus e power 2 lambda plus etc. Okay. So, this identity holds inside your formal power series algebra or the ring. Okay. So, this is the only thing that we need. So, we will be working in this setting. So, one can actually view everything happening inside this z bracket lambda, but it will be comfortable to work with this formal power series ring or algebra. So, this is where we will be doing all our computations. Okay. So, what we are interested in? So, for example, we are interested in the character of this V of lambda. So, let us set some notation. Let us call this chi lambda to be the character of V of lambda. So, by definition, this is the finite sum of dimension of V lambda mu e power mu, where mu comes from the weight of this V of lambda. So, since this weights of the V of lambda, it is a finite set, this sum is indeed finite sum. So, one can view this as element of z bracket lambda. So, this is indeed element of z bracket lambda. So, in particular it is element of q double bracket lambda by 2. So, this is something we will be actually. So, we want to understand what will be the character in terms of some known factors. So, for that purpose, let us actually define these Weyl sums. So, given lambda, let us say dominant. So, we define this S lambda plus rho. So, this is the numerator of what you find it in the numerator in the Weyl character formula. So, this we call it Weyl sum. So, Weyl sum, of course associated with this lambda. So, this is defined to be the summation, this is the numerator sine of sigma e power sigma lambda plus rho, sigma comes from Sn plus 1. So, this is the definition of S lambda plus rho. So, now with this notation we can easily rewrite the denominator identity. So, if you rewrite the denominator identity, you can see that S rho is nothing but the sum side of the denominator identity, which is summation sine of sigma e power sigma rho, sigma comes from Sn plus 1, which is same as e power rho times product 1 minus e power minus alpha, alpha comes from delta plus. So, recall that rho is the Weyl vector. So, this is called the Weyl vector. So, which is by definition it is a off sum of positive roots. Okay. So, in particularly one can actually rewrite this S rho in terms of these positive roots as follows. So, S rho, so if you rewrite, if you substitute e power rho by e power of times summation alpha, alpha in delta plus, then this identity becomes the following. So, this is product e power of times summation alpha, alpha in delta plus, alpha comes from delta plus. So, this times 1 minus e power minus alpha, sorry this, so this product is outside. So, this is product alpha in delta plus 1 minus e power minus alpha. Now, what we can do, we can take out this e power of alpha and then put it inside. So, this actually becomes S rho equal to product alpha in delta plus e power alpha by 2 times 1 minus e power minus alpha, which is exactly same as product e power alpha by 2 minus e power minus alpha by 2, where alpha runs over delta plus. So, now you can see that this is why we are enlarging that group ring to this lambda by 2 group ring generated by lambda by 2, and we are going to invert these elements the whatever there in this product. So, that is why we need to consider this as element in the formal power series. So, this is indeed element in the formal power series. So, because we also need to talk about the inverse of this S rho, and it is easy exercise for you to think about this S rho indeed has inverse inside this formal power series. So, S rho inverse exists in this formal power series ring. Okay. So, that is obviously going to be the product of the inverse of 1 minus e power minus alpha and then this e power minus rho times e power minus rho. Okay. So, now we want to actually define some terminologies, because in the Weyl's character formula you can see that so that Weyl character formula is written as ratio of two factors that defined like S lambda plus rho and S rho. So, they are indeed some skew symmetric elements. So, because of that it is good to define what is symmetric element and what is skew symmetric element. So, let us just recall the definition. Okay. So, it is easy to see that to define this symmetric and anti-symmetric or skew symmetric elements, one can work inside Q of bracket lambda. So, there is no issue. So, let us define only for those elements. So, there is this natural action of Sn plus 1 on this Q bracket lambda. So, you take W and then apply it, acts on e power lambda by e power W lambda for all lambda in capital lambda, and then you just simply extend this linearly to all the elements of Q bracket lambda. So, there is no issue in that. So, in particularly Sn plus 1 acts on this Q bracket lambda. Now, if you actually take some element f inside Q bracket lambda and it is said to be symmetric, if it is invariant under the action of this Weyl group. So, that means W f should be f for all W in W. So, this is the meaning of this f is being symmetric. And of course, what is anti-symmetric or skew symmetric? Whenever you apply W, so you need to get the sign outside. So, that is called anti-symmetric. So, this is the definition 1, the definition 2. So, f in q bracket lambda is said to be anti-symmetric or skew symmetric if when you apply W on f you get sign outside, sign of W f for all W in W. So, W is nothing but Sn plus 1. Okay. So, this is the definition of symmetric and anti-symmetric elements, and we know actually that the elements that are defined here S lambda plus rho, they are all actually anti-symmetric elements. So, it is simple exercise that I will leave it to you to do. So, for any lambda in capital lambda plus, we have that S lambda plus rho is anti-symmetric. Okay, that is because the way the S lambda plus rho is defined using the alternating summation. So, it must be anti-symmetric. So, now we can try to understand what this symmetric and anti-symmetric means in terms of the coefficients of f. So, let us try to understand that. So, if we write f as summation a mu e power mu, mu comes from lambda. Suppose f is symmetric, let us say f is symmetric. So, then it means when you apply some sigma f for any sigma in W, which is Sn plus 1. So, sigma f should be equal to f. So, that means f is equal to summation a mu e power mu, mu comes from lambda, which is same as summation a mu e power sigma mu, where mu again comes from lambda. So, since e power mu's they form a basis, so you have to compare the coefficients. So, now if you compare the coefficients, you can see that a mu is same as a sigma inverse mu for all mu in lambda and sigma in Sn plus 1. So, that means f is symmetric translated into this coefficients being same for the orbit of this mu. Okay. You fix the mu and then take orbit of mu under the action of Sn plus 1, all these coefficients a mu should be same. So, now what is anti-symmetric means? So, here is a small observation or a lemma. So, this f is anti-symmetric. One can prove that if and only if you can write f as g times some g times s rho for some symmetric element g. Okay. So, this is something easy to prove. So, let us actually prove this. So, if f is g times s rho, then it is clear that f must be anti-symmetric. Okay. If you take symmetric element times anti-symmetric element, then you get back symmetric element. Okay. So, I will leave that as exercise. If f equal to g s rho for some symmetric g, then that implies that f is anti-symmetric. That is because symmetric times anti-symmetric is anti-symmetric, and it is not hard to prove that symmetric times symmetric will be symmetric, and symmetric time anti-symmetric times anti-symmetric will be symmetric. Okay. So, with that sign rules, you can see that this is indeed anti-symmetric. So, what is about the converse? So, let us start with f is being anti-symmetric. So, write f in terms of the basis element, f equal to summation a mu e power mu, where mu comes from lambda. So, then it is clear that sigma of f is nothing but sine sigma of f. So, this actually indeed says summation a mu e power sigma mu, mu in lambda is same as summation sine sigma a mu e power mu, mu comes from lambda. Okay. So, now one can compare the coefficients of this e power mu on both sides. So, then it is easy to see that. So, the coefficient of e power mu here is going to be a sigma inverse mu, which is same as sine of sigma a mu on the other side. So, now if you think about it, okay, so one can actually replace this as follows. So, sine sigma inverse a sigma inverse mu is equal to a mu. So, this is how one can replace. So, this is same as saying if and only if a mu is equal to sine of sigma a sigma mu. So, whenever you apply Weyl group element, then you get again sign outside for the coefficients as well. So, now if you actually take the orbit and then you can actually rewrite this. So, f you can rewrite as summation. So, mu comes from now modulo the action of this w, the coset representatives of the action of w on capital lambda. So, you can just take it from there, this first summation, then the second summation will be sigma comes from w sine. So, a sigma inverse of mu e power sigma inverse mu. So, this is going to be the sum. So, what we are trying to do here, okay, we are fixing one coset representative and then we are running over all possible orbits of that mu with respect to w. Okay. So, then this is exactly equal to summation a mu, because a sigma inverse mu is nothing but sine of sigma times a mu. So, I can take out a mu, then it will be just summation sine of sigma e power sigma inverse mu, where sigma runs over w, where mu runs over lambda modulo w. So, this is what we get when we replace the relations using this relation, the coefficients a sigma inverse mu. So, then what we get f equal to summation mu runs over lambda mod w a mu. Then this, if you think about it, if you run sigma in w, sine sigma is same as sine sigma inverse. So, sigma running over w is same as sigma inverse running over w. So, this you can rewrite as sigma in w sine sigma e power sigma mu. So, now using that you can easily see that this f is rewritten as summation a some lambda plus rho, lambda comes from this lambda plus and then s of lambda plus rho. So, basically if f is anti-symmetric, then we have actually shown that this is exactly equal to summation a lambda plus rho times s lambda plus rho. So, in some sense we have done some change of basis and then we have written in terms of this Weyl sums, f as in terms of Weyl sums. So, now it is not very hard to prove that s rho indeed divides s lambda plus rho. Okay. So, of course, this question makes sense where it divides, and one can prove that if you think about it, this is indeed divides inside Q bracket lambda. So, this even indeed happens inside Z bracket lambda. So, that is what our Weyl character formula says. Okay. So, if you rewrite the Weyl character formula, so it basically says for lambda in capital lambda plus. So, if you actually take the character of the irreducible module, then that is given by S lambda plus rho divided by S rho. So, that means not only that S rho divides S lambda plus rho, that is exactly given by the ratio is given by chi lambda, but we know that this chi lambda is element of Z bracket lambda. So, using the Weyl character formula, you can immediately see that S rho divides S lambda plus rho, and that ratio is indeed lying inside Z bracket lambda. But you can easily prove that S rho indeed divides S lambda plus rho. I will actually outline the proof in a minute, but then how do you use this to conclude the result that we wanted? Then you can write F as summation A lambda plus rho S lambda plus rho divided by S rho times S rho. You can write it like this, lambda in lambda plus. Now, this tells you that F is equal to G times S rho, where G is nothing but summation A lambda plus rho S lambda plus rho divided by S rho, where lambda runs over capital lambda plus. And since S lambda plus rho and S rho both are anti-symmetric elements, it is clear that G must be indeed symmetric element. So, F is written as G times S rho, where G is symmetric and S rho is anti-symmetric. So, this is something what we wanted to prove. So, this proof indeed tells you that if you start with anti-symmetric element, that anti-symmetric element indeed lies in the span of all these Weyl sum elements S lambda plus rho. That is also kind of clear from the argument. Now, I will just actually tell you like how to prove this S rho divides S lambda plus rho inside this Q bracket lambda, and indeed it is easy to work inside Q bracket lambda by 2, and it is not hard to prove that because this is the group algebra corresponding to this lambda by 2, and lambda by 2 is a lattice. So, you can easily prove that this is actually isomorphic to some Laurent polynomial algebra over Q, okay, in finitely many variables. So, that exactly the transcendental degree will match with this dimension of this lambda by 2. So, if you think about it, this is indeed U of t. This is unique factorization domain. Okay, I am not going to do all those things here, but this is U of d. Now, one can rewrite S rho as follows. This is exactly product of e power alpha by 2 minus e power minus alpha by 2, where alpha runs over delta plus. And now, because this is indeed U of t and this is a product of actually some factors. So, now it is enough to prove. Okay. So, these factors are actually relatively prime. So, this e power alpha by 2 minus e power minus alpha by 2, they are alpha in delta plus, they are relatively prime elements inside your U of t. And now, this is the first observation. The second observation, that e power alpha by 2 minus e power minus alpha by 2, this indeed divides your S lambda plus rho. Okay. And that is something very easy to prove, that is not very hard. So, that actually tells that when you actually take this product e power alpha by 2 minus e power minus alpha by 2, that must divide this S lambda plus rho. So, this proves that this element, anyway the ratio must be inside this Q bracket lambda by 2, but you can compare the coefficient and then immediately see that the ratio must lies inside this Z bracket lambda. So, that I will leave it to you to think about it. Anyway, we are going to prove the character formula. So, the character formula also tells you that this is true. Okay. So, we need to actually prepare some more results in order to prove the Weyl character formula. So, we will actually do that slowly in coming classes. Okay. So, maybe I will stop here with this result. Okay. Then we will continue with the proof of the Weyl character formula in the next class. Thank you.